Let's do an example. We've got an input x of n. Let's make it a exponentially decreasing input like this. And it is causal, it's right-sided, it's multiplied by u of n. And we're going to put it into a FIR system. Whose h of n is composed of a length 2 system, 2 and 6. And n equals 0 and 1, and that's it. And we would like to analyze what we get out. Now, for the record, we know that y of n, because this has this u of n component to it, y of n is going to be equal to a transient part that decays or goes away, plus a steady state part. That would be the same as if we had plugged this in for all time without the multiplied by u of n. Our goal is to find the output, y of n, and we'll talk about two methods to do it. The first method, the exact method, uses z-transforms. So let's figure this out. We can always find the exact output using either, we have a number of tools. One is time domain convolution. Time domain convolution would be fairly nasty mathematically here. So instead, we're going to use z-transforms. We're going to find the z-transform of this, which you can look up on a table and read it off. And then we're going to find our z-transform of our system. And our z-transform of this system, since it is finite length, m equals 1, since it's non-zero up to a maximum of 1. Remember, it's because it's FIR, that means our n of the system has to be 0. And that's the same thing as saying that the denominator of h of z is just plain old 1. And it's the same thing as saying that our current value of y of n depends upon only our current and past inputs and not on past outputs, because otherwise it would be an infinite impulse response filter. So all these are true for this particular system and its FIR. And our h of z, we can read it right off, is 2 plus 6 z to the negative 1. And that means that our output is the product of these two. It's always the input times the transfer system and system transfer function. Of course, this is only true in the frequency domain. Y of n is not equal to the product of these two. It's equal to the convolution of these two in the time domain. But we can do that. We can multiply these two to find the z-transform of y of z. So this is what we would like to now inversely transform to find y of n. So for this particular y of z, we can see our upper number is always equal to m, so m equals 1 and n equals 1. That's for y. We already figured out that m is 1 and n is 0 for h, for our verb, for our system. But for our output, our signal, n and m are the same number, and that means it's not proper. We want to have n strictly greater than m for it to be proper, because we're going to have to put this thing through eventually some sort of partial fraction decomposition to look it up. So in order to make it proper, we're going to have to divide. Now, when we divide, this is the one where we swap the order. If you're just going to divide to find the first couple of values of y of z, we would divide through here without changing the order. But as part of finding the partial fraction decomposition, as part of finding the inverse transform, we need to do the division. So let's see. What times negative 1/2 z to the negative 1 gives us 6? It'll have to be quite a bit, right? It'd have to be minus 12. And that will give us 6 z to the negative 1. I'm going to multiply them directly. I'll just do the correct signs here. And 12 minus 12 times plus 1 would be minus 12. So just like we learned way back in grade school, we'll subtract the bottom from the top. Because adding these numbers is easier for me, I'm going to subtract bottom from top by flipping the signs and adding them. So this gives me 0, and this gives me 14. And now I can write it. Without flipping things again. So this is our result. So I'm going to write that a little bit bigger over here. Y of z, once we divide it out to make it proper, is equal to minus 12 plus 14 over 1 minus 1/2 z minus 1. And so we can do the inverse transform by sight and say that's equal to minus 12 with an impulse at n plus 14 times 1/2 n u of n. So that's the exact answer to our problem. Let's do it a different way. Let's use method 1, in which we use the steady state approach. So remember to do method 2, which uses the steady state approach. What we're thinking about is we've got some sort of complex exponential. And it's going to go into our system. And what we get out is going to be the exact same thing as what we put in, times our system evaluated at z equals j omega naught. So this first number here, this is just a complex number. It's like a gain. And the second thing, this is our function. And it's the same thing as our input. Okay. So we need to find a way to recast our input, x of n, from 1/2 n u of n. Now we're going to pretend it's sinusoidal, it's exponential steady state. So we're going to get rid of that u of n. And we need to find some way that we're going to recast this 1/2 to the n as this e to the j omega naught n. We'll need to find out what our omega naught is. So we want to get rid of this e, right? So we'll try taking the ln of both sides. And hopefully that'll give us something easy to work with. So let's see, if we take the ln of something with a power, that n comes out. And the ln undoes this e, so that just gives us j omega naught n. We've got n on both sides. And so now we can solve for our omega naught. It's just ln of 1/2 over j. So now we know what our omega naught is. We know what our h of z is, right? Our h of z is equal to 2 plus 6 z to the negative 1. You know, it's the same thing as saying our h of e to the j omega is equal to 2 plus 6 e to the minus j omega. Just putting in, wherever we see a z, putting in e to the j omega. So now we've got the two important parts to figure out our problem. We've got our complex frequency, and we've got our system. And so we believe that the full and true output, y of n, is going to be equal to some transient part that will decay away, plus the steady state part. And that steady state part we can figure out using this method up here. It's just going to be equal to whatever our input is, which is 1/2 raised to the n u of n times our h of e to the j omega evaluated at whatever our omega naught is. So let's see if we can figure that out quickly. It's 1/2 to the n u of n times, let's see, this gives us 2 plus 6 e to the minus j. And now we find what our omega naught is, and our omega naught we said is this. So that's going to be equal to ln of 1/2 all over j. So the j's cancel. And now we get 1/2 n u of n times 2 plus 6. Let's see, we've got e to the minus ln of 1/2. So now our question is, what is e raised to the minus ln of 1/2? Well, if we didn't have this minus here, it would be easy because e undoes ln. But with that minus, it's a little confusing. Let's try writing this a different way. I think everybody agrees this is true. And so therefore, e undoes the ln, so that gives us 1/2 to the minus 1. And that's the same thing as saying 2. There's other ways we could have figured that out too. We could have also said ln of 1/2 is equal to ln of 1 minus ln of 2, using the rules of lns, and that ln of 1 is 0. So that just gives us minus ln 2. And so we could have rewritten this top thing by saying e raised to the positive ln of 2, which is clearly 2. So either of these ways would have worked. So this complicated thing up on top just boils down to this. And let's see, 6 times 2 plus 2 is 14. So that gives us some transient behavior plus this, which is our steady state behavior. And let's see what this is. What I'm saying is that since this impulse response here has a capital M of 1, that this transient part will only exist between n and m. In other words, will only exist between 0 and something less than 1. Well, that can only be n equals 0. And so it means that for n greater than 0, we have y of n equaling 14 1/2 n u of n. And compare that with what we have on our left, that except for that one difference at n equals 0, our output is indeed equal to this. So this is the steady state part, and this is the transient part.